Now these pictures are drawn on 2D, therefore they're talking about a single variable. But it's a multivariable function, then we have to talk about second derivative, slightly more involved. Recall your multivariable calculus course. Assume that you still remember or can quickly brush up your memory about that. If a function, let's say, of just say 2 variables, once you get hang of that, it's same as many variables, is quadratic, x squared plus xy plus y squared. Okay, xy are single variable, but is a function of both variables. Now, what is a second derivative of a multivariable function? It's not a simple expression anymore. It's not a number. It's a matrix. With partial derivative of this function with respect to x squared and with respect to y twice, okay, and with respect to both x and y, with respect to both y and x. This is the matrix. You have to take partial derivative with respect to x and y, and in general we say, given a function f of variables x1, x2, of xn, if we look at the partial derivative with respect to xi and then with respect to xj, this is the ijth entry of a matrix. That matrix is called the Hessian matrix, or in short, the Hessian of the function. So in this particular case, it is very simple. We take derivative twice with respect to x, we get 2. With respect to y, we get 2. With respect to x and then y, or y and then x, the same thing for us is 1. Okay, so this 2, 1, 1, 2 is the Hessian of this particular function, and this is the general definition right here. The ijth entry of the matrix is partial f, partial x, I, and then partial f, partial x, j. So how do we make sense out of saying that a matrix is positive? It's not that the entries of the matrix are positive, but it's about whether this matrix eigenvalues are all positive or non-negative. And you can check that this matrix eigenvalues are all non-negative, and therefore this function is a convex function. But in general, we say a function is convex if satisfy the second derivative test, where the Hessian matrix thus defined is so-called positive, semi-definite. And a matrix being positive, semi-definite means all the eigenvalues are positive or non-negative. Now you may wonder, what if my function does not have a second derivative? Its Hessian matrix doesn't exist. Some functions are not smooth enough that you can take derivative twice or even once. Well, it turns out that that's fine too. I can have a function with a sharp corner. Okay, at this point we don't have a second derivative, but we can still define a function as convex or not, and this would be a convex function. However, since all our functions throughout the entire course are smooth enough that the Hessian matrix exists, we will just follow this definition. Okay. So, minimizing a convex function, which we know how to detect now, subject to a convex set, is a convex optimization. And least square is a special case because least square minimizes a convex quadratic function subject to no constraints.